This is a problem from the International Math Olympiad 1979. It says if we have an alternating series, finite, 1 minus half plus 1/3, all the way up to plus 1 over 13, 19, where if the denominator is odd, then we have positive terms. If the denominator is even, then we have negative terms. And if we denote it as P over Q, then we want to show that 1979 divides P. Of course, we have to, here P, Q, and R are both positive integers. And of course, we have to require P, Q to be co-prime. If otherwise, look, if they're not co-prime, then I can just say, okay, you give me any fraction, like 2 over 3. I can just multiply both the top and bottom by 1979. No problem. Still same fraction. So now I can just denote it as P over Q. Right? In that case, P and Q are not co-prime. But I can still claim that P as 1979 times 2 still divisible by 1979, no problem. So that's why we have to require them to co-prime. So if we just, first of all, let's rearrange it. So P over Q equal 1 minus half plus 1/3 all the way plus 1 over 13, 19. Then I can just simply group all the positive terms. 1 plus 1/3 plus 1 over 5 all the way 1 over 13, 19 minus all the negative terms grouped together. I have 1/2 and 1 over 4 all the way up to until 1 over 13, 18, I believe. So therefore I can just insert here 1 over 2, 1 over 4, 1 over 6, right, so on. 1 over 2, 1 over 3, 1 over 4, 1 over 5, all the way 1 over 13, 19. Previous was 1 over 13, 18. And of course, I'm going to have to minus the same thing, minus 1 over 2, minus 1 over 4, and so on and so forth. So I can just combine, I can put minus 1 over 2, minus 1 over 4 in here. So all I have to do is multiply every term by 2 in this bracket. So I have 1 plus 1 over 2 and 1 over 3. I get 1 over 6 becomes 1 over 3 and all the way times 2. So 1 over 6, 5, 9. So in this case, we can just cancel out these terms. 1 plus 1, 1 over 2, 1 over 3, 1. So I'm left with 1 over 660. Right? That's the term right after 1 over 659. So 1 over 661 all the way. 1 over 13, 18 plus until 1 over 13, 19. Right? So again, rearrange. 1 over 660 plus 1 over last term, 13, 19 grouped together, plus 1 over 661 plus 1 over 13, 18, all the way until and so on and so forth. Right? Finite to many terms. So in that case, I actually have the pattern is clear. The pattern is that every time I find a common denominator, then I just add those two numbers up. And that'll give me exactly 1979, right? Same here, 1979. Every time I have 1979 on the top. 1979, right? So after I factor 1979 on the numerator as a common factor, I'm left with just a sum of fractions. And those fractions, first fraction is 1 over the product of those two numbers. Second fraction is 1 over product of those two numbers. But then I can just denote it as P naught over Q naught, where Q naught is perhaps a product of those numbers, right? This number, this number, this number, this number. Common denominator. Right? So I also know that if I use the fundamental theorem of arithmetic, I can see that Q naught, if rewritten in a unique factorization of prime numbers, right, then I can have P1 to the power of alpha 1 times P2 to the power of alpha 2 all the way PR to the power of alpha R. Right, so the positive powers, positive integer powers, unique primes. And so I can also claim that because every number denominator is smaller than 1979. Smaller than 1979. Therefore, because every number here can be written into unique factorization prime numbers, right? So which means every prime number in here must be strictly less than 1979. So that tells me that every prime number in here has to be also strictly smaller than 1979 and also bigger than 0, bigger than 1. Because even though there are many numbers here, right, but every number is smaller than 1979, so the prime factor has also to be smaller than 1979. Right, when you find a common denominator, multiply them all together. I just combine the common prime numbers, whatever. But regardless, right, we still have every prime number here must be smaller than 1979, right? So also notice that 1979 is also a prime. This is verifiable. You can just divide by 1, divide by 2, all the way up to divide by the floor of the square root of the number. They're easily verifiable. So which means how can we tell 1979 and Q naught are not simplifiable? How can we know that? If they are simplifiable, if they're reducible, the only possibility is that Q naught has to contain a prime number that is exactly 1979. Otherwise, they're not simplifiable. Right? But does Q naught contain prime factor of 1979? No. Because we were just shown that Q naught, right, every prime factor of Q naught has to be strictly less than 1979. So in fact, 1979 is not simplifiable with Q naught at all. So altogether, of course, we assume P naught and Q naught are also coprime. Right? As long as we add all the fractions all together, and if they're not coprime, we can use Euclidean algorithm to simplify them down until they are coprime. Right? This is easily doable. And also, P naught, Q naught, coprime. 1979, Q naught, also coprime, right? Not reducible. So that means altogether, indeed, it is no longer simplifiable. So 1979 times P naught as P, right? This exactly denoted P over Q. Right? 1979 times P naught is just P. So indeed, divisible by 1979.